Good afternoon, everyone. Welcome back to our Solidity webinar presented by Nehemiah STEM Research. My name is Muhwezi Donald Hastings, and today we'll be moving on from what we covered yesterday, which was visibility, to interface. And basically we're going to be looking at how to talk to smart contracts or other smart contracts, and basically how smart contracts talk to each other. We'll be diving deep into interfaces in Solidity. How does your DeFi protocol interact with Uniswap? How does your NFT project use Chainlink prices? It all starts with understanding interfaces, basically. So we'll break down what they are, why they're essential, and how to use them. So this session is going to cover what an interface is and its strict rules, and how to create your own interface for any contract. Yeah, so we'll look at that, and then of course we'll have an example code, and then we'll break that down as we go through the code. But before we begin coding, let's define a few things, a few concepts that need to be defined before we can start. For example, you need to know what an interface is, though we've looked at it in our previous sessions. So interface in Solidity, an interface is a contract abstraction. Basically, it is like a blueprint or an API specification that defines what functions exist in another contract, but not how they are implemented. It contains only the function signatures, that is the name, parameters, return types, and visibility, without any actual code inside the function bodies. So why do we use interfaces? For intercontract communication, 2 for security, 3 standardization, and 4 decoupling. Now, on the basis of intercontract communication, interfaces allow your contract to call functions on other deployed contracts without needing their full source code, but only their interface. And then on the basis of security, they provide a known, safe set of functions to interact with, reducing the risk of calling unexpected functions. And then for standardization, interfaces are the foundation of standards like ERC20, ERC721, and so on and so forth. Any contract that implements the standard interface can be interacted with in a predictable way. And then finally, for the use of decoupling, your contract doesn't need to know the implementation details of the other contract, so it makes your code more modular and upgradable. So those are one of the key reasons that's why we use interfaces. And then we could define some key rules of an interface. Number 1, no implementations. That is, functions can only be declared, not defined. Function visibility. So that is, all functions must be declared as external. And then another key rule is that there are no state variables. You cannot declare state variables in an interface. Besides not declaring state variables, it doesn't have constructors. So interfaces cannot have constructors. And then another major key rule is that interfaces can inherit from other interfaces. So they have the ability to inherit. So with those definitions, I'm going to look at contract here, or a file, a Solidity file that's going to have two examples. One will be basic. So those examples are basically contracts within this file. One will be basic, and another, and I think I'll try and make a real world example. So we can then start coding and then have a look. Just give me a second. Okay, let's get started. So let's start with the basic one. So this will be a simple contract that we can let's say we'll interact with using an interface. This is a public state variable, which basically creates an automatic data function. Okay, this is it. Let's look at what's happening here. So we have a contract, a normal implementable contract called counter that we declared from line 6. So yeah, that's basically, like you can see in the comment, it's a simple contract that we will interact with using an interface. The contract has a state variable, a public state variable of data type and signed integer 256. So since it's the state variable is declared public, the Solidity compiler will automatically create a getter function for it named count. So this is crucial for the interface. And then we have a function inside the function increment, or a function called increment, and it's an external function that modifies a state. So this is the function that we will call through the interface. And then all the way down here to line 23, these comments are basically trying to explain what I was doing. Yeah, so as I was saying, line 22, we have interface iCounter. The keyword interface, that's the definition of an interface, which is named iCounter. Now, in that interface, we have a function called count. So this is the function signature for the auto-generated getter function of the public count variable. This is function count. So notice that it has a semicolon instead of like a function body where we usually do this. So it just has this semicolon here. And it must be external, like we said. The visibility of auto-generated getters, and then it must be view because it doesn't change state, and then it must have the exact same return type. So just like here, yeah, the same type. And then we have line 29 function, an increment, a function called increment. So this is the function signature for the increment function in the counter contract. Yeah. And again, it's just a declaration with ending with a semicolon. It doesn't have a function body. And also again, it must be declared external. And then line 36. So we have a new contract that will use the iCounter interface to interact with counter contracts. Yeah, with the counter contract. And in that contract, my contract here, it's called my contract, we have a function called increment counter. This function expects the address of a deployed counter contract. And then line 46, iCounter underscore counter increment. So this is basically a type conversion. It takes a value of type address and then tells the Solidity compiler to treat it as what's the word I'm looking for? To treat it as a contract of type iCounter. So this is how we apply the interface to a specific contract address. And then this part, yeah, so what I just explained was just this part, yeah, and then this part here, once the address is cast to the iCounter type, we can call any function declared in the interface on it. So this transaction will modify the state of the contract at underscore counter. Then line 51, function, the get count function, address underscore counter external view, all that is a view function to read data from another contract. And then line 55, return iCounter. So same concept, it casts the address to iCounter and then calls the count getter function defined in the interface. Since it's a view function, we can return its result. And then line 62, interface Uniswap v2 factory. So that's an interface for a real world contract, the Uniswap v2 factory. In there we have a get pair function, so it takes two token addresses, yeah, and returns the address of their liquidity pool pair. And then line 72, interface Uniswap v2 pair, is an interface for a Uniswap v2 liquidity pool pair contract. In that interface, 75, line 75, we have a get reserves function. That's the function that returns the current reserves, which are the liquidity amounts for both tokens in the pair. And then line 84, contract Uniswap example. We've declared a contract that demonstrates using the Uniswap interfaces. And then from line 87 to 89, so these are hard-coded addresses of the already deployed Uniswap. The DAI and I don't know if you call it WETH or WTH contracts on Ethereum mainnet. So these are constants. And then line 92, function get token reserves. That's a function that will return the reserves for the DAI and WETH pool. And then line 94, address. Pair is equal to Uniswap factory get pair, and so Uniswap, this part here, let me highlight it. This part casts the hard-coded factory address to the Uniswap v2 factory interface type. Yeah, and then this part get pair DAI WETH is using the interface and then calls the get pair function on the actual deployed Uniswap factory contract. So it returns the address of the DAI and WETH pool or WETH pool, whatever you want to call it. And then line 98, so again, this part here casts the pair address we just found to the Uniswap v2 pair interface type, and then this calls the get reserves function on the actual pool contract, and then this part here is a tuple assignment. The function returns 3 values. We capture the first two, which is the reserve or reserve index, reserve 1, and ignore the third, which is the timestamp, by leaving it blank. So that's why there's a space here. And of course it returns the 2 values on line 101. So in summary, what all this does, or what it shows, it demonstrates the use of interfaces in 2 scenarios. One being a basic example, which is the counter, which shows how to create an interface for a simple counter contract and use it to call that contract's functions from another contract, the other contract being this, my contract. And then it also demonstrates a real-world example where we've been talking about Uniswap v2 factory and Uniswap v2 pair. So it has showed how to use existing interfaces to interact with live deployed protocols like Uniswap v2 to read on-chain data, which are the token reserves. Yes, so let's compile and try and interact. Now I'm not sure if Remix will allow us to this environment will allow us to deploy and get those real values, the real Diane with result values. But let's try and see. So let's deploy the counter contract first. Yeah, it's the counter, and then we note the address. Copy that somewhere. I've copied its address just so you know. And then we deploy my contract. So let's try calling the get count, right? But it's expecting an address, so we'll put in the contract address of the counter, right? Remember, we're in the my contract now, and the address I copied earlier, I copied it. So we need to call the get count and then pass that address of the contract we deployed first, and we should, let's see the value, but I'm expecting it to drop as 0. Yeah, 0. So that's working. And then we can call the increment counter. So this one, it should just send a transaction. Let me check that from here, the terminal. Transaction mined and execution succeeded. So if we call the get count now again, it should return a 1, yes. So like I was saying, for the real world example, I'm kind of doubting because I think it needs an IDE like Hat or Foundry, forked from Ethereum mainnet to work with real addresses and that. But let's deploy and then try and call the get token reserves function to see if it will pass in real of values. Yep. Yeah. So yeah, that's not. It's just an IDE issue. But yeah, this is how interfaces work basically. Yeah. Thank you for tuning in. This has been a STEM Research webinar. Solidity. Don't forget to like the video, share it, leave a comment, and then subscribe to the channel. Have a blessed evening.